Chapter 26, Theory Video 5, we are going to discuss Lenz's law. So now, earlier we discussed the Faraday's law and we deduced the value of the EMF that is generated as a result of the induction, electromagnetic induction. Now we are going to talk about the direction of the EMF. In another sense, what we are going to understand is which end of a wire or a coil is going to be positive, and the other what is going to be negative. So that is what we understand. That is what we figure out using Lenz's law. So now, if we use the Fleming's right hand rule, then it gives us the direction of the current that is caused by the induced EMF. So this is actually a little bit of this is considered to be a general law, which is not exactly what we use to talk especially about EMF. So we need a specific law. That is what that is the purpose of Lenz's law, because you can actually find the direction of the current using what we discussed earlier. But then why do we need Lenz's law? You might ask that question. So the reason why it is needed is what we are going to figure out in this. So electromagnetic induction, we have to learn about the origin of it. How does this current originate? So here, when we think about this particular diagram here, there is a straight metal wire XY. We push it downwards through a horizontal magnetic field of flux density B. So we are pushing it down like this, in this direction. So then what happens is, in the free electrons get a push. So what happens to them is the electrons start moving downwards. So if there is a movement of electrons, that results in a current. So as a result, because we say that electrons are negatively charged, because it is a positive charge movement we are talking about, the current is flowing upwards. The conductor is pushed downwards. As a result, the electrons or the current is said to be flowing upwards. Now, when we have a current that is flowing across a magnetic field, or we know that all the principles that we have learned will come in unison. It is not different from one another, because these electrons have gained that kinetic energy. The motor effect, the Fleming's left hand rule will come into effect here, because the electron is moving, because there is a current, because there is electrons. We say that electrons are moving the current. Now in this situation, we discussed that what happens is, when the electrons are pushed downwards, we say that the conventional current is flowing upwards. So there is a current. So then, using this current, we generate a force, magnitude BeV, using the left hand rule. When there is a current, there is a force generated. Then we can find out in which direction the electrons are pushed. Electrons will be pushed from X to Y. So what basically happens is, let me explain it again because you might have got confused because of the upwards and downwards story. Now what happens is, this conductor is pushed downwards along with the electrons. When the electrons flow, so the electrons are moving. When there is an electron, there is a current. So as a result of the current, there is a force generated, the motor effect. So the motor effect results in the electrons being pushed in this direction. I hope that makes sense to you. So basically, that force in turn uh, is the current that is flowing through. So there is a electrons being pushed from X to Y. So we say that the current has been induced to flow in the wire, and the direction of the conventional current is from Y to X. From Y to X. That is the direction of the current, as opposed to the movement of the electrons, because we are talking about the conventional current. Now, when we get Fleming's right hand rule, we can figure out the motion, field, and current, and we know that they are in compliance. That is, they agree with one another. So then, what happens is, when EMF is induced, the EMF induces a current because the electrons are pushed by the motor effect. So as a result, we say that electromagnetic induction is a consequence of the motor effect. Then at Y, we can see at this, in this diagram, in the earlier diagram, that is this diagram, we can see that at Y, if the electrons are moving to that edge, electrons will get accumulated at Y. Therefore, it is going to be the negative end of the EMF, and X is going to be the positive end of the EMF. So when it is connected to a circuit, electrons would start flowing out of Y around the circuit, and again will return to X. So then this diagram 26.21 will show how the moving wire is going to be equivalent to a cell or any other source of EMF. So there is a current flowing back to front, just like a cell. I hope that makes sense. Now we are going to discuss about forces and movement. Electromagnetic induction is the process by which we generate most of our electricity. When we turn a coil in a magnetic field, so all of this hydroelectric power or diesel power or wind power, all of these forms that we use in our country uses a generator or a turbine. So this turbine is turbine uses electromagnetic induction to generate this electricity. So the mechanical energy that we put is transferred to electrical energy. So using this understanding, or using this relationship also, we can figure out the direction of the current. So this deducing the direction of the current is going to be an important part in your questions. So here what we have is we are pushing the north pole of a magnet towards the coil of the wire. So this generates a current in the coil. So we need to realize which direction it is going to be. So now in this situation, the first one is incorrect. The second one is correct. How it is so? So when this is pushed towards the coil of the wire, so the field is in which direction? And the field is in, you have to figure out which direction it is going to be, and then you have to figure out what happens when you bring the magnet close to this. What happens to this? The coil is going to become an electromagnet. One end becomes the north pole, the other becomes the south pole. So then what happens is, now in A, if the current is in the direction that is shown, then what happens is, the coil end or the nearest pole of the coil is going to be the south pole. Then what would happen is, if you let go of the coil, it would get attracted to the magnet. So then what would happen is, the magnet would also accelerate into the coil. Then what happens is, there would be a force of attraction between the two, and that would continue to increase when they come closer. But without us giving any energy at all, we are not doing any work, but there is a lot of energy that is being created because the magnet is moving into it. So the coil, we don't have to move the coil. It is this, because this is the south and the north pole, this will get attracted into this direction, this will get attracted to this direction. Then when it goes through without us doing work, there is electrical power generated. That cannot happen. So then what should happen is, when you bring in the second situation, this is the correct situation. What happens is, when we bring it closer, the north pole of the magnet is pushed towards the coil, and the current caused by the induced EMF, so it cuts the conducting wire that generates electricity, and as a result, the end of the coil, the closest to the magnet, will become north pole. There would be repulsion. Now because there is a repulsion, we have to do more work to push it into it. So this additional work done is what is converted into electrical energy of the current. So as a result, the principle of conservation of energy is intact in this situation and is not violated. So there is a form of energy that is being transferred, because we cannot create energy out of nothing. I hope that makes sense now. So in the next diagram, in this situation, what happens is, when we push a wire in a downward direction through a magnetic field, there would be a current caused by the induced EMF. So we need to figure out in which direction. Now this is a current across a magnetic field. So as a result, there will be a force, again motor effect. And if we use Fleming's left hand rule to figure out in which direction, we will see that it is the motor effect force is in upward direction. So we are applying a force, pushing it downwards, the motor effect force is upwards. So as a result, what happens is, in the first situation, so the force is pushing downwards, motor effect force is also pushing downwards, so they get attracted. So that cannot be. So then current would again increase exponentially without any energy input. So as a result, again in this situation, the correct form is the second one. We have to do work against the force. So these two situations you need to understand really well, and you should be able to explain it if they give you questions of that sort. Question number 13 and 14 will let you know how questions will be should be answered. Let's write down a note on this. Lenz's law. Lenz's law is used to figure out the direction of the induced EMF. The electromagnetic induction generates as a result of the movement of a conducting wire along with free electrons in it across the magnetic field of flux density B. When the electrons start moving downwards, as shown in below diagram, a current is generated upwards. This current that flows across the magnetic field bring about the motor effect, generating a force of magnitude BeV, capital B simple EV. In the following situation, using Fleming's left-hand rule, we can figure out that the direction is from X to Y. Direction of the movement of electrons is from X to Y, and the direction of conventional current is from Y to X. Leave a line, leave a line and write. When this system is connected to a conducting wire, just like any other source of EMF, electrons will start to move from the negative charged point to the positively charged point. I hope you understand this. So the electrons are moving in this direction. So as a result, the current flows in this direction as shown by them, because the conventional current is the direction of the current we are talking about. Write down. when trying to figure out the direction of the current, we need to understand that the direction of the current will depend on work being done against the effect of the magnetic field. So in earlier situation also you have to draw these diagrams, figure 26.20 and figure 26.21 to so that it is understood. So now I want you to draw these diagrams as well to show that it is used the direction is found out using the idea of doing work against the magnetic field. There should be work done against the magnetic field as shown below. If the coil or the wire becomes attracted or gets attracted to the magnet without any energy being provided, electrical energy would be produced, because that is an impossibility. In the first diagram, the closest end of the coil should become a north pole, and when work is done against it, that work done would be converted to electrical current, electrical energy. I hope you understand. I want you to do question number 13 and 14. Now we are going to go into the general law for induced EMF. So we say that Lenz's law summarizes the general principle of energy conservation that we discussed. That means the energy is conserved because only the work that is being done is turned into electrical energy. It does not, without doing any work, it does not create energy out of nothing. If that is a possibility, then we can simply make sure that magnet continues to go through a magnetic loop, and we will forever get energy. But that is not a possibility. We have to do work against the magnet. As if you make it into a pool or a circle, we can continuously make a magnet move through it and forever get energy. But that is not a possibility. So we say that the direction of a current caused by induced EMF or EMF or electromotive force is such that it always produces a force that opposes the motion that is being used to produce it. So if the EMF is produced by a motion that is coming inwards, then the force that it produces is outwards. So they meet one another, the opposing forces meet one another. So the overcoming of these two forces will bring about the energy change. If that is the opposite of this, then we would be getting energy for nothing. So we say that any induced EMF will be established in a direction so as to produce effects that oppose the change that is producing it. So this important statement is something that you need to remember. Any induced EMF will be established in a direction so as to produce effects that oppose the change that is producing it. So the EMF is being produced so that the direction of the effect is in the opposite direction, right? In any experimental situation, this will be proven because this is a law. Now, in this 26.3 diagram, that is something that we have met earlier, I suppose. Yeah, please locate this diagram, then you will be able to see that. Now we have used the sensitive ammeter in a circuit, so that gives the direction of the current when it is moved in and out. Then if we connect a battery to this coil to allow a large and a constant current to pass through in the same direction, we will see actually that poles are going to be at the end of the solenoid. Now, if we move a north pole of a magnet to the end of a solenoid, we will see then that that end of the solenoid will become a north pole at that point. If the north pole is moved out of the solenoid, then the solenoid will have a south pole at that end if it is moved out. So basically what it says is, now there is a solenoid. If we move a north pole in, then what happens is this will oppose it by making it a north pole. But if we are pulling it out, then it will oppose it by trying to attract it by making it a south pole. I hope that makes sense. Then we summarize this, the electromagnetic induction using Lenz's law by the equation by adding a negative sign. E equals negative delta n phi upon delta t. So E is the magnitude of the EMF and the minus sign shows that the induced EMF causes effects to oppose the change producing it. So the the effect that is producing the EMF, it is opposed by the direction of the EMF. The minus sign comes because of Lenz's law. So it is very important that we need to understand and emphasize on the fact that energy is conserved, because if not, we will be able to obtain energy without giving any energy at all. Write down a note on this. Lenz's law summarizes the principle of energy conservation. Then write down the definition. Any induced EMF will be established in a direction so as to produce effects that oppose the change that is producing it. Leave a line and write. For example, when you will have to draw this 26.3 with the changes. When a magnet is moved into the diagram below, you have to make sure that you have included a battery to give it a constant current. We will observe that there would be poles at the end of the solenoid, at the ends of solenoid. If the north pole of the magnet is moved into the solenoid, that end of the solenoid will become a north pole. If the north pole is moved out, then to oppose that end of the solenoid will become a south pole. Write down the equation. E equals negative delta n phi upon delta t. Leave a line and write down Lenz's law proposes or indicates that the induced EMF causes effects to oppose the change producing it. To oppose the change producing it. If you have understood, please do question number 15 and 16. In the next video, we will go to the last part of this lesson.